Hello everyone, today I want to talk about the Schrödinger equation, specifically the time-independent Schrödinger equation, and how we can find a solution to that differential equation, because at the end of the day, the Schrödinger equation is just a differential equation, and it's actually not hard to solve. So if you recall what the Schrödinger equation is, it looks something like this. Now, it comes off the fact that energy, total energy of a system, can be defined classically as the total kinetic energy plus the total potential energy, which will denote T and V respectively. And the Schrödinger equation basically says that the energy of that system, while also incorporating this probability idea that we call the wave function, okay, that equals a whole bunch of junk, which is the potential energy times the wave function, okay? And then it's going to be minus this constant, h squared over 8 pi, or I guess not really a constant because the mass of your particle could change, I suppose. The m is equal to mass here, and then times the second order derivative, which I'll denote in a different color, the second order derivative of the wave function with respect to x, where x is a position. So this is a one-dimensional idea, and let's take the following example to express what this is trying to say. Okay, so if we consider a particle moving in just one direction, okay, this is how complex it gets, where we have to dumb down our proof to just one dimension. Okay, we have, let's say we have two bounds that the particle cannot get out of. Let's say a one-dimensional box. Okay, so the particle might seek to move from here to here, and it can't go past that. And let's call this 0, and this a arbitrary length L. So the particle can move in one direction from 0 to L. And here's that particle there, little happy particle. Let's give him a smiley face. Okay. So what we're going to say here is that the potential energy, if the particle were to be, say, here, or here, or here, or here, let's define that to have an infinite amount of potential energy, right? Because it would be impossible for the particle to escape the box. So how we're going to write this is that V has a restriction on its domain, and it looks something like this. So if return infinity, if x is less than 0, or x is greater than L, and return 0 if the opposite is true. So x is contained within the bounds of 0 and L. Okay, that's the idea that we're going for. Okay, so if this particle moves out of the bounds of the box, it's going to have infinite potential energy. Okay, so my question to you is, how can, if you've taken differential equations, you'll understand that this in fact is a differential equation because we have a second order derivative mixed in with some functions of the wave function. So how can we solve for this? Well, we need to make an assumption. In differential equations, it's a very common tactic to find a function that that we can manipulate in such a way that we can solve for just the wave function. And that's what we're going to do. It's very extensive here. You might have learned about like an integrating factor, for example. That's a good example of DE trickery. But yeah, let's get into it. So we're going to assume that a solution takes the form of a mix of sine and cosines, because at the end of the day, wave functions are waves, right? Let's say it's a linear combination almost, not really a linear combination, but a pseudo-linear combination of a sine wave and any multiple of it, A, times B cosine kx. And what this is saying is, this is basically defining any wave you could ever think of, okay? In some amount of A and B, you could get any wave that you wanted. Okay, so let's say that the wave function takes this form. Well, then what does that say about the derivative of the wave function with respect to x, okay? Because we're plugging in a position and we're getting out a wave out of it, which is the wave function. So what's the derivative of that? Well, this is going to be ak cosine of kx, okay? And then this is going to be minus bk of sine kx. Okay. And we could actually make a simplification now, but what I'm going to do is just get all the math out, all the derivatives, and then we'll make that simplification in a second, and it actually will turn out very nice for us. The second derivative of the wave function with respect to x is negative ak squared sine of kx minus bk squared, not Burger King, squared. It's going to be bk squared cosine of kx, okay? Now, what simplification can we make? Well, understand that what we can do to solve for specifically one of these b, a's, or k's, we can make a little bit of a simplification, okay? Because what we want to do in the grand scheme of things is understand what is in differential equations. If you've never taken the class, the half of the challenge is solving the differential equation. The second half of the battle is finding what a, b, k is, right? These things. Well, remember the idea that if we set x equal to 0, the wave function will go to 0, because the wave function tells us what is the probability. I guess I should have explained this at the beginning. A wave function is basically synonymous with the probability of an electron. Probability of E minus, we'll say. All right, probability of an electron. That should make sense. You probably learned that in Gen Chem. Just wanted to reiterate in case you're a little lost. If we have a particle here, first of all, it's not going to happen because the particle cannot escape the box, okay? It's stuck, it's confined to the box, and we could find it even a little micrometer. I'll even exaggerate here. We could find it here, but as soon as we hit that wall of the box, the wave function goes to 0. You're not going to find an electron there. It's just not possible, okay? So what can we do? Well, let's take our initial function and let's say, okay, we know that for x equals 0, the wave function equals 0. Okay, so if the wave function equals 0, well, let's think about it. If we plug in cosine of 0, well, then we get b. And if we plug in, for x, 0, sine of 0 is 0. So this is 0 plus b. And that tells us that b is simply equal to 0. So what we're going to find is that this whole side here is literally just going to cancel out. So we can just ignore these terms here. And that actually makes it quite nice for us because now instead of finding 3 constants, we only have to find 2, which is a and k respectively. Okay, so what we want to do now is find what is a and what is k. And I believe what we're going to begin with is k. Okay. So this is going to get quite extensive here. Oh my god, I'm rereading my notes. Okay, let's do it. Let's return back to our... Oh, before we do that, we need to define this. A simple observation and simplification we can make to the math here. This should be squared. looks like this. Negative, and then notice that it's a k squared, and we can simplify the a and the sign, because if you remember, our initial idea is that this is some sort of sine wave, okay? Shifted whatnot, any wave defined as a sine wave, and we can simply take that component here and simplify that as our function, okay? That's an important distinction to make. But let's observe something. Let's say that, and we made an assumption that inside the box, the potential energy is 0. So all the energy of this particle is totally kinetic. We're assuming that there's 0 potential energy because we want to make things simple for us. It could be that the particle has some sort of kinetic energy. We just are going to assume in our case, or there is some potential energy, but we're going to assume in our case that this particle has no potential energy and it's all kinetic. That's what this stanza is saying here with respect to potential energy. Inside the box, 0 potential energy, all kinetic energy. When we get out of the box, it's all potential energy and it's an infinite amount. Okay, sorry, I just had to get that out of the way. Let's go back to our initial equation here, this guy, and we're going to take our second order derivative of the wave function with respect to x and plug it in here. Okay, so if you're curious what I'm writing out, that's what I'm doing. I'm substituting this guy for this, okay? So I just want you guys to keep that in mind as I do it. It's pretty obvious, but you know, you don't want to get lost on these kind of things. It's important. And then times negative k squared times the wave function. And remember, if our potential energy is 0 in the domain of which we are evaluating this in, well, then this term goes to 0, okay? So we don't need it. And it's going to be equal to the energy of that system times the wave function, okay? Pretty simple. Notice the negatives cancel, and if we want to solve for k, let's first say that k squared is equal to E times the mass times 8 pi squared over h squared, meaning that k is simply the square root of all that junk, okay? So k is simply the square root of the energy of that particle, the total energy of that, times the mass, times 8 pi squared over Planck's constant squared. So if you know the energy, you know the mass, you can find k, okay? That is pretty simple. Now, what we're going to do is a little bit of a trick to understand what the energy, the total energy of the particle is. Because that is important, as we will find out here. So let's do that. What is E? Because we need to know how we can express E as a function. And it turns out that it's going to be dependent on this mass term, but also our bounds, 0 to L. To what extent is L? We're going to see that relationship here. Okay, just a little aside, I guess, to the whole finding the solutions. If you want to find E, what you can do to find E is you can say, if a general solution to the wave function is A sine kx, well, simply replace k with the square root of this guy. Over h squared times x, and we evaluate whatever that sign is. All right. Recall that at x equals L, the wave function is equal to 0, okay? That should make sense. You're never going to find a particle at L, right? At x equals L. Okay, well, what does this mean? Well, this means that 0 equals a sine of em 8 pi squared over h squared times x. All right. This implies that this relationship is true, but we need to take a closer look at which term is going to be 0, because, well, they could both be 0, but one of them has to be 0, right, for this equality to be true. So either sine is evaluating all the time to be 0, or a is always 0. Which one do you think it is? Okay, I'll give you a second to think about that. Well, it's not going to be a. What does it mean if a is 0 all the time? If a is 0 all the time, that means for any x, I input any x value. This a value is going to always put sine to 0, and that's going to imply that there's no wave function at all, right? If I go here, an arbitrary value, that is saying that the wave function is 0. Or if I go here, the wave function is 0. But we know that the wave function has probability all in here, so it doesn't make any sense. I hope that you can see that. A just can't be 0. So that means that sine has to be 0. What makes sine 0? Any multiple of pi n, okay? So what we're going to take is we're going to take this argument here of sine, and we're going to say that the square root of e times m 8 pi squared over h squared times x must equal some multiple of pi. All right, that should make sense, right? Because for sine to go to 0, sine needs to be evaluating at a pi integer. Okay, I guess not an integer, but some n integer of pi is what I was trying to say. Okay, and it turns out that this n is actually where our energy levels come in for the atom that we're looking at. So the different energy levels of that particular atom you're studying, that is going to be the different levels of it. Okay, so let's now solve for E. Hopefully this isn't too difficult for you guys. We're going to square both sides, right? How did x get there? Hold on. Oh. My apologies. I was confused why x was there. This should be L, the distance of your box. And then this is equal to pi n. I was like, that doesn't make much sense. Okay. We figured it out. Square all your terms to get rid of the square root. Em 8 pi squared over h squared, and then there's also that L squared term, right? Because this is outside of the radical, it's going to get a square to it. Pi n squared, okay? All right, so we have identified that. This should also be a squared term here, pi squared n squared. That makes sense. So if we solve for E, we're going to see the pi's are going to cancel out. We're going to get, geez, that is really messy. Let me fix that for you guys. E equals n squared h squared over 8l squared, okay? Hopefully you can see that here. Okay, what we're going to do now is pretty extensive, so I'm going to save the work. It's just algebra. We're going to plug E in right here, and we're going to solve for, sorry, I shouldn't say here. We're going to plug it in up here, and we're going to solve for a generic wave function, okay? So this is going to get messy. Bear with me. We're going to skip all the math. You can prove it if you want. It's just simple arithmetic. It's nothing that crazy. But when you simplify that, that you're going to find that the wave function for any n level in that atom is going to be equal to A sine n pi x over L. Okay, pretty simple. Now what we're going to do is find A, and to understand how we're going to do this, let's understand what phi can be, the wave function can be evaluated from, integrated. If we integrate the domain of which is the domain of our box, right? So if we take an integral of the wave function squared dx, we say that this probability from 0 to L, the contents of our box, is in unity, which means that its probability just comes out to 1. Okay? That shouldn't be too hard to see. If it's in unity, the probability of finding an electron anywhere in that space is simply just 1. Okay? So if we have this generic form and we plug it in, what we're going to find is the integral from L to 0 of a squared, I'm just pulling out the a there, sine squared, okay, of, and remember the inside doesn't get affected here, n pi x over L, alright, dx. And remember, if you are having trouble solving this integral, just remember that sine, this is a little hint, sine squared of x is equal to 1 minus cosine of 2 theta over 2. Sorry, I guess it's not theta in this case, it's x, my apologies. 1 minus cosine of 2x over 2. Simply plug that in and integrate. You're going to find that the integral is, let me grab my work here because I'm too lazy to do it. You're going to find that it's a x over 2 minus cosine minus h pi, geez Louise, h pi sine of 2n pi x over L. Alrighty. Over L. Alright. And we're integrating all of this from 0 to L, and we're saying that this area is definite and it is 1, okay, because it is of unity. The probability is centered around 1, and just so we're clear, it's saying basically if I look here, from here, maybe at this point here, the wave function is 0.3, which would be 30%. Okay, just wanted to point that out for you. I'm sorry, this should be a squared. Okay, so let's consider what happens when we plug in our bounds. Well, here, simply 0 being our lower bound, that's not going to matter, it's going to cancel out. We're going to get a squared L over 2. Okay, and this little term here, let's just consider 0. Obviously, it goes to 0. Sine of 0 is 0. L takes L over L here, and it cancels it out. We're left with 2n pi. For all n, sine will be 0, so we can simply ignore this term here. This term goes to 0. Okay, so it simply says that a squared L is equal to 1. L over 2 is equal to 1, which implies that A, well, it doesn't imply, it shows that A is simply equal to the square root of 2 over L. All right, so that's how we find L. This means that the wave function for a time-independent wave function, yn, is equal to square root 2 over L times sine of n pi over L, the confines of that one-dimensional box, times wherever your position is relative in that domain, and that is the wave function. So a lot of math we just did, but hopefully you see the idea. Let's just overall recap what we did, because we did quite a bit. I mean, in my notes here, I have at least, I don't know, 3 pages of notes. It's not pretty, but that's 4 pages of notes. Oh my god. On solving this differential equation. You could make it much simpler, but this is the most thorough way. The wave function tells you the probability of finding an electron out of 1. Basically, if I look at some place, what's the probability that I'm going to see an electron there? Okay, we know that energy of a particle is equal to its total kinetic energy plus its potential energy. In other terms, in the quantum world, Schrödinger has defined this as such. This is called the Schrödinger equation, the differential equation that models the energy of a particle times its wave function. We made up a hypothetical scenario where we have a particle contained within a box from 0 to L, okay, such that the potential energy inside the box is 0 inside the box, but outside the box the potential energy skyrockets to infinity because it simply just cannot possess existing outside of the box. We define the wave function to be some sort of sinusoidal wave, which is kind of a superposition of 2 waves, sine and cosine, with arbitrary scaling factors, or I guess I should say multiplicity factors of a and b, and a scaling factor of k. We define the derivatives, d wave function dx, okay, and we found the second order derivative. We understood that we could simply cross out b, because at x equals 0, the wave function is 0, which implies that if we plug it in simply to the wave function, we find that b is equal to 0. It takes care of b. And then we did some math to find what k was by substituting in the second order derivative. Very simple. And then we sought to find the energy of that wave such that we could plug it in to the wave function here, which is going to help us find the term A, which we found by understanding that if we integrate across our box's length, it's in unity, which means that the probability of finding an electron in there must equal 100%. That makes sense. We did some math. We evaluated the integral, and we found A to be the square root of 2 over L. We plugged that in, and here is our wave function. So the solution to the time-independent wave function looks like this, and thank you for watching. Bye-bye.